So it's my great pleasure to introduce Uday Shanbhag, who is now a professor at the University of Arizona, so he has traveled a bit, and but he has a very strong research record, a famous guy in the stochastic programming community. So it's really a pleasure to have him today. We'll speak about probability maximization via Minkowski functionals, and I will not spend more time. The floor is yours, Uday. Thank you for coming with us today.
Thank you, Fabien, and thank you, Walter, and the rest of the organizers, and Eric for inviting me and for holding this wonderful set of talks. I wish I could attend, more of them. Unfortunately, I've been teaching a little more than I'd like this semester, so things have been a little more hectic. But thank you once again for organizing this remarkable collection of talks. So this is actually work with my doctoral student, Afrouz Jalil Zadeh, who's now at Arizona, and my collaborator, Constantino Lagoa, who's in the electrical engineering department at Penn State, and his doctoral student, Ibrahim, who's now moved back to Turkey, but I don't have the correct affiliation, so I just left it as Penn State. Okay, so this work pertains to probability maximization, and I'm going to relate it to the more general problem of chance-constrained optimization as we, as we get towards the maybe 60% of the talk. So this is the problem that we're interested in. We're interested in maximizing our function f, where f is defined as a distribution function parameterized by a decision vector x. So I'm going to be optimizing over some set x script, where x script is a closed and convex feasibility set. And this boldface k, which I'm going to refer to as k of x, is just the set of psi in some k script such that c of x zeta is non-negative. Okay, sorry, the set of zeta in k, I apologize. And k script is a compact and convex set. Okay, and I'm going to assume that c is a d-dimensional. C goes from Rn times Rd to Rm, so it's an m-valued function, and zeta is a d-dimensional random vector with a prescribed distribution p. Okay, so that's a problem of interest. Now, as you can see, this is a special case of the chance-constrained program, which originates from the work by Chance, Cooper, and Simons in '58, and Chance himself. And this is an extremely well-studied area, and so there's no way that I can do justice in terms of capturing all of the research in this area, but clearly the important work, the important pieces of work can be traced back to the work by Prokopa, Miller, and Wagner, and as I mentioned, it subsumes this probability maximization problem and has broad applicability in addressing reliability and robustness. Okay. And what I want to do in the first 5 to 8 minutes is say something about the tractability question in chance-constrained optimization, and then provide a motivation for our present work. Okay, so let's consider the set x script of p, where x script of p is essentially a probability constrained set, right? And x script of p is, and these are classical results, right? X script p is convex if this psi has a log concave distribution and f is defined in this affine form, right? There are other assumptions. I'm just going through some of them. And this is some work by Lagoa, Lee, and Schneiser, where they actually showed when f of x psi satisfies this structure and a comma b has a symmetric log concave density, and for suitable choices of alpha, again, you can claim that x script of p is convex, right? However, what you need is to enable efficient computation, you need efficient computability of the chance constraint, and you need convexity of the set, right? And so tractability holds in some select settings, and there's a wonderful description in the work by Prokopa in '98. But in general, this problem is intractable. Okay? And so that has motivated an effort to develop convex approximations, right? So in particular, can we compute feasible suboptimal solutions to CCP, right? And so one avenue has focused on using scenario-based approximations, and the precise question here is how, if you replace the chance constraint by an approximation where you have n realizations of the random variable f of x of psi, and you introduce these constraints f of x psi j for j from 1 to n. The question is, how large does n have to be to ensure that x star n, a solution of CCP sub n, is feasible with respect to the original problem with a suitably defined probability? Okay. And a partial answer was given by Calafiore and Campi in 2006. But this even for problems where little n is relatively small, let's say 200, capital N in terms of number of realizations that you need can be quite large. So, and that's not particularly surprising. The alternative approach has been forwarded in terms of building analytical approximations. So suppose psi j are independent and zero mean. F of x is affine and psi, say defined in this particular fashion. You can actually get some understanding of the violation probabilities. Okay? And this has motivated this idea of a convex approximation of CCP. And what that does is it basically replaces the chance constraint by an inner approximation. Okay, and so this is work that has been followed by Mendowski in 2000. That has been initiated by Mendowski in 2003, and there's been subsequent work with Shapiro and others. Again, it's a subset of work in this area. But again, here what I want to emphasize is that a solution of this problem provides a feasible solution of the original problem in some sense, and but there are no guarantees in terms of suboptimality with respect to the original problem. A third approach has been using smoothing-based approximations, right? So essentially, you can write down this probability using the indicator function, right? But in general, as you know, this leads to a discontinuity, and there's been an effort to employ smoothing techniques. And this goes back to the work by Ermoliev, Norkin, and Wetz in '95, and others. Okay, so there's a wonderful paper by Norkin, which is unpublished, I believe, but is on the YASA website, where he looks at the optimization of probability functions. And that, I believe, came out in '98. Okay, but I want to just spend a little bit of time on that, right? So you have if you essentially look at the smoothing of that indicator function using what is often referred to as convolution-based smoothing, and you can approximate. And so this is the paper I was referring to. It's not 98, it's 95. You can approximate f by f epsilon, where the indicator function is captured by the smoothing-based approximation, and this allows us to make several claims regarding f epsilon with respect to f. Okay, so in terms of pointwise convergence, the concavity properties that are inherited, and the subdifferentiability properties. Right. So there's been a lot of effort to actually utilize these types of smoothing techniques to compute stationary points. And notable amongst that is some work by Frank Curtis in 2018 and his co-authors, and most recently by Ying Kuei, Junie Liu, and Zhongxi Pan in 2021, which is actually quite a remarkable piece of work where they've analyzed the directional differentiability and developed avenues for addressing relatively general problems and contending with the non-smoothness and non-convexity of these problems. Okay. There's also a lot of work by Shabir Ahmed, Jim Lukey, and Alex Shapiro using integer programming techniques. So essentially, what happens is you approximate the chance constraint using a combination of sampling and the introduction of binary variables, and you're able to essentially use these types of sample average approximations to provide both convergence statements in terms of the sample average, the SAA solutions, as well as rate guarantees. Okay, so this is work by Shabir Ahmed all the way back in 2009, and again, there's been a lot of work. Okay, so what I want to point out is what you see in most of these efforts is that either you have convex approximations which provide feasible solutions with high probability, but there are no optimality guarantees with respect to the original problem, or you have smoothing-based approximations which often lead to non-convex optimization problems. You provide approximate solutions of the smooth problem. Again, there are no error bounds with respect to the original problem. And so our effort was motivated by the need to compute an approximate global minimizer of the original problem, right? Not in its full glory, as in, but we're going to look at subclasses of these and then talk about how we can introduce extensions. Okay? And then feel free to stop me at any point. I've mentioned to Fabien that I won't be monitoring the chat, but if there are questions that emerge, please just feel free to stop me. Okay. So I want to remind the audience of the problem that we'll be focusing on. I'll be focusing on the probability maximization problem, where f is a distribution function parameterized by a decision vector x. X script is a closed and convex set. And I'm going to be defining k of x, which is what zeta has to lie in, as a set of zeta that lie in k script such that c of x zeta is non-negative. Okay. So let's continue. Okay, so I'm going to be looking at two particular settings, right? So the first setting is where c of x zeta is defined as 1 minus zeta transpose x raised to m, where m is a positive scalar, or tx minus zeta. Okay, and these are two settings. Now they might look a little bit restrictive, and we'll talk about extensions of these as we proceed. Okay, and you can see that, for instance, the second of these is fairly common, where you actually have you have an affine constraint on x. Okay. Okay. So let's start. And what I'm going to the way we're going to proceed with this is we're going to first focus on setting A, and then I'm going to spend a bit of time on setting B, but the analysis is quite similar. Okay. So the assumptions on k script and x script, as I mentioned, x script is a closed convex set. We're going to assume it's bounded for the remainder of the talk. And k script for the time being is assumed to be a compact and convex set and is symmetric about the origin. Okay, and I'm going to, and this is an important assumption. I'm going to assume that zeta is uniformly distributed on the set k script. Now, this assumption I want you to keep an eye on, and we're going to be talking about weakening this assumption as we talk about the extensions. Okay. Okay, so the main idea that of this work is to be able to show that under some conditions, this probability can be written as the expectation of a continuous function. Okay. So this integrand of this expectation is going to be shown to be continuous. As you know, you can actually do this when you have an indicator function, but that leads to discontinuities. What we show here is under some conditions, you can find that this probability can be written as an expectation with respect to a suitably defined density. And this density allows for, this density is with respect to, this is a distinct density that we construct, and I'll show you how it's constructed. And what is also important to note is that this object on the right, the expectation of f of x psi, essentially has some convexity properties, and I'll make those precise. Okay. And that provides a pathway in terms of efficient computation. Okay. So essentially that's the main idea. So this probability is essentially written as the expectation of f of x psi with respect, which is essentially the integral of f of x psi with respect to this density p tilde of psi. Okay, and this is the definition of f and of p. Okay, but let's go through the analysis of it. Okay. So before that, I want to just define the Minkowski functional. So given a set k script, the Minkowski functional associated with the set k script is going to be defined by the norm k script, where the Minkowski functional associated with zeta is defined as the infimum of t such that zeta over t lies in k script. Okay, so this is relatively well known. So now I'm going to just talk about how, the proof sketch, because in some sense that provides you with a deeper understanding of how we obtain this result. So remember what k of x is. K of x is defined as the set of zeta such that c of x zeta is non-negative, right? Now in this particular case, c of x zeta, if you remember, for the setting A is 1 minus zeta transpose x raised to n. Okay. Now, if c of x zeta is non-negative, that's equivalent to saying that zeta transpose x is less than equal to 1. Okay. And in addition, what we have is zeta has to lie in K script. So these are the two requirements. So you can write K of X as the intersection of the set of zeta such that zeta lies in K script and the set of zeta such that zeta transpose X squared is less than 1. Note for this part I've assumed that M is 2, but you can actually generalize it. Now the set K script is convex, compact, and symmetric, and the Minkowski functional defines a norm. And hence it is a positively homogeneous function, which I'll use an acronym PHF to refer to. And so by definition of the Minkowski functional, zeta lies in K script if and only if zeta squared, the norm zeta squared with respect to K script is less than 21. Okay, so this relationship holds. So which means that this set can be replaced as follows. So I can write K of X as the set of zeta such that zeta transpose X norm squared is less than 1 intersection the norm squared with respect to K script is less than 1, which is of course the same as saying the max of these two is less than 1. Okay. Now, once you observe this, you can see that since both zeta transpose X squared and zeta squared with respect to the norm zeta squared with respect to K script are both positively homogeneous functions of degree 2, the function g, which is defined as the max of these two, is also a positively homogeneous function, right? And that's a crucial observation. Okay, so that observation allows you to invoke a result by l.s.c, which was proved in 2012, and I'm going to just provide that result. Okay, so the result by 2015, apologies. So what l.s.c proved was that if h is a positively homogeneous function of degree p, right? So this is what we have on the left. Okay, so this h is essentially what we have. We have our g. This is given by the integral with respect to, so this original integral is with respect to d zeta. It's equal to an integral with respect to d psi, where you replace h of zeta by h of psi, and you introduce this exponential function, where you take this exponential function as the e raised to minus the max of all of these components, g1 to g sub l. Okay, where omega is defined in terms of these gk's, right? And so this is a fair amount of technical detail, but what you want to take from this is something quite simple, right? What you want to take from this is, on the left, you've taken this K of X, you can write this expectation. So the original expectation is this one, right? So this original probability event is this one. You can write it as the indicator function over K of X. Okay, that's the probability event. And because you have that zeta is defined using a uniform, is uniformly distributed over this set K script, you have to divide by the volume of K script, right? So what you have on the left is quite, follows directly from the definition of the probability, and what you have on the right follows from the result by l.s.c. And it follows because K of X is defined using these positively homogeneous functions, and it's defined as essentially the integral of e raised to minus g of psi d psi. Okay, and that's the crucial result. And that basically paves the way for everything else that we're going to do, right? And now when you look at this, what you notice is, oh, it's e raised to minus g of psi d psi. I can multiply and divide by some positive density and essentially write it in this form, right? So I had it in this form where I have e raised to minus g of psi. I now multiply and divide by, in this particular case, by the Gaussian density. And what I'm able to come up with is f of x psi, right? And essentially, what is this? This is really the expectation with respect to a suitably defined Gaussian density. But I could choose some other density if I so desire. But it turns out that choosing the Gaussian density is important because it allows you to ease the analysis of it. Okay, and remember, this Gaussian density, I'll come back to this later, essentially represents, so this Gaussian random variable is what we're going to be using for purposes of computation. Okay, so effectively what happens is f of x, which is the probability of zeta lying in K of X can be written as the expectation with respect to a suitably defined Gaussian density of f of x psi. Okay, and f of x psi is essentially this function. Okay, so that's the first result, right? That's the first result. And what it does is it allows us to rewrite the original probability in terms of the expectation with respect to some other Gaussian density. Now, once you have access to that, the next question is that can you recover some sort of convexity property? Well, it turns out there's a result by by leveraging some results from convex bodies. What you can show is that the reciprocal of f of x is indeed convex. And this comes from a technical result by Bobkov in 2010. Okay, and then he used properties of log concavity. Okay, and the requirement that zeta has a symmetric log concave density. Okay, so if you have that, then you can show that the reciprocal of the original probability is actually a convex function. Okay, now, so I want to recap these two results. So you can actually think about the analysis later if you want, and we can talk offline. But what you want to remember from the set of descriptions in the previous two or three slides is the original probability is written as the expectation of an integrand with respect to a suitably defined Gaussian density, and then the reciprocal of this expectation, this probability, is convex in the decision variable x. Okay, those are the two results. Okay, now once you have that, you can actually refine these. So if you look at the paper, we're able to actually specialize these results to the regime where K script is an ellipsoid. So there are things that you can do once you have these further specializations on K script. Okay. Now what happens when you look at setting B? So when you have setting B, and if you assume that zeta is uniformly distributed on K script, where K script is symmetric about the origin, right? It turns out then that you can actually you can transform that problem into a convex problem just by using known results on log concavity. So you can actually claim that the negative of the log of f of x is actually a convex function, right? So that is actually known. It's not something that we've been able to just leverage prior results for that. But what we have shown is that for this setting B, I can do something very similar. So this probability can again be written as the expectation of a suitably defined f of x psi with respect to a suitably defined density. And the ideas are similar. They're not obviously the same. You have to do the analysis is slightly different, but the ideas are very similar. So you essentially take the event and you show that you can rewrite the probability as the indicator function over some set which is defined using positively homogeneous functions. Once you have that structure, then you can directly invoke the result by Lazare to show that that probability is indeed an expectation of some f of x psi using a density that you can choose. Okay. So once you have that, you can write the first setting as a convex optimization problem, where the optimization problem isn't necessarily simple. It's essentially a compositional problem. So what you end up with is 1 upon the expectation is convex. In this particular case, you have the negative of, so in this particular case, you have that the negative of the log of the expectation is convex, and that's what you operate on. Okay. So now, once we've done that, the next question is, how do you solve this optimization problem? Okay. So solving, and I'm going to focus on setting A, but setting B is similar. So if you look at it, you think that a prototypical stochastic approximation scheme would suffice, right? So you can essentially think about, what would a prototypical stochastic approximation scheme be? Essentially, what you do is you compute a Clark generalized gradient of. So if you remember, what you have is this function. Now, unfortunately, if you want to get So of course, if you want to actually get a Clark generalized gradient of f, which is what I'm going to call d of xk omega k. If you compute this, what you get is minus g of xk omega k divided by the square of the expectation, right? Now, unfortunately, so d of xk omega k is a conditionally unbiased estimator. But the problem is to compute it, you need access to the expectation, and you don't have that. Okay, so which means that you cannot efficiently compute a conditionally unbiased estimator, right? So this problem is afflicted with bias from that standpoint, and what you need to do is use a different avenue. Okay, so let me first talk about the avenue, and then I'll just go back to the assumptions. So the avenue that we use is essentially a variance reduced approach, where what we do is we essentially replace the expectation squared, or rather the expectation, with a sample average using a zeroth order oracle. So I have an oracle that produces f of x psi for a given x, right? I can get n such realizations. Now remember, unlike in other stochastic optimization problems, in this particular case, I'm generating samples from an oracle that I have control over, right? So this is just the Gaussian density. So the amount that you sample is less relevant. There isn't some sort of, you're not working with a finite amount of data. Okay. And so, okay, so you get some approximation of the expectation, and you get an approximation of the gradient. Okay, or in this particular case, the Clark generalized gradient. And then this W bar here just refers to the dk minus capital dk, where capital dk is essentially defined as follows, and little dk is essentially going to be the true gradient. Okay. Now, again, so I'm going to assume that I have access to a zeroth and a first order oracle. That assumption is perfectly fine, given the fact that I have an associated Gaussian density, so I can basically simulate using that. Okay, so using that, I can and using the structure of f of xi, because I have an analytical form, I can prove that the conditional second moment of these of W bar G and W bar F, which is the different sequence associated with the first and zeroth order oracles, can be suitably bounded, right? And you can actually show, because you're using variance reduction, that this is of the order of nu f squared over nk if you're using nk samples, and nu g squared over nk if you're using nk samples of the first order. Okay. Now, once you have that, then you essentially use standard approaches to go through the analysis. And what you're able to show, unsurprisingly, is that the expected suboptimality diminishes at the rate of nearly at the rate of 1 upon square root k. It's slightly worse by some delta. And you have a sample complexity result, which is of the order 1 upon epsilon raised to 6. As I said, in this particular case, the sample complexity is of little relevance because sampling is cheap and there is no, there's no budget on the sample, if you will. Okay. You can also almost show convergence under suitable assumptions on the step length sequence. And these choices, of course, are not, you don't need to, they're not reliant on some obscure Lipschitzian parameter or something of that sort. Okay. And so now what we wanted to do was we wanted to assess to what extent do these results allow us to recover the original solution, or do we get good approximate solutions? So what we did in our first set of tests, we applied this problem to the vehicle routing problem. In this particular case, we assumed that this is setting A, okay? And we looked at 4 sets of problems, and this computation is just a subset of the work we've done. And what you notice is that we ran 20 replications, and what we're able to see is that when you compare this to the case where you use the integer programming framework, which is guaranteed to get you the global minimizer and the limit, you can see that you get very close to these solutions. Now, I should note that the integer programming approaches, of course, take a lot more time. So we ran this integer programming approach for 10,000 seconds and we terminate with whatever gap we have. Okay. And so you can see that as we spend more and more time, we get increasingly accurate solutions of the global minimizer for setting A. If you look at setting B, so setting B looked at the regime where you had so where you had zeta transpose x is less than negative alpha, and what you notice there is, again, in this particular case, we actually have access to the true optimal solution through a different avenue. And you can see that we compared this with a standard fixed mini batch scheme. Okay. And what you notice here is, again, we do very well. Okay, do very well compared to the global minimizer. You can look at these results from the standpoint of the trajectories, and the green trajectory here represents how the regularized variance reduced stochastic approximation scheme does. And really what you should focus on here is just the iteration complexity, because sampling is cheap and we don't have any kind of restriction on number of samples that we can use. Okay, so these are the numerics, and what I want to do now is talk a bit about extensions. Okay, so in terms of extending these types of findings, what you notice, the first aspect of the problem that we imposed an assumption was the choice of distributions for zeta, right? And so now I'm going to weaken that. So now let's look at the regime of symmetric log concave densities. So suppose the density of zeta is log concave and symmetric. In particular, it satisfies the property of log concavity and symmetry. And there are examples of these, right? I'm not going to be spending time on these examples. Normal, the Laplace density, and so on. Okay. And you're going to see that we're going to look at the chance-constrained version subsequently. So I want to just talk about this regime. And so this is well known, and this result I think goes back to Procopa, but it's listed quite clearly in the monograph by Shapiro, Dencheva, and Ruzinski. And essentially what this says is that this should be CJ, I'm sorry. If the inner function is quasi-concave in both its arguments, and the original distribution function is as a log concave distribution, is log concave, then G, this constraint function, is log concave on D, which is where D is appropriately defined. Okay. And so what that allows you to do is that if G is log concave, then the log of that is concave, and you can essentially get convexity of that set. Okay. Okay, so that's what we're going to leverage. But the issue is that when you have log concave symmetric densities, we can't directly apply our framework. And so how do we extend our framework to accommodate these types of densities? So I'm going to look at what are called super level sets of log concave symmetric densities. And so this is the super level set associated with P zeta, where T represents the threshold. Okay? So S of T is the set of zeta such that the density is greater than T. Okay. And so this is what on the right you have what the density looks like. As I mentioned, it's symmetric about the origin. Okay. And the density itself can be written as the integral of the indicator function with respect to S of T and defined at zeta. Okay. So basically this indicator function takes on a value 0 if you're outside the set, and the value 1 if you're in the set. And beta is the maximum value that this density achieves. Okay. So now P sub zeta is defined in this form. And so then let's go back to our event. Our event in the setting A was defined as the set of zeta such that the norm of zeta transpose x is less than or equal to 1. Right? So I can then define the original event as the integral of the density with respect to this, the density over k of x. Okay, that's just a re-articulation of what you have in the left. Now, based on the way I define P of zeta is defined in this form, right? It's specified as follows using the using the super level sets, I can replace P of zeta as this indicate, using this definition that leverages the super level sets, right? And now I can actually interchange the integrals under some assumptions. And what you find is, and of course I've skipped some analysis here, but I'm just trying to give the audience some understanding of how one would extend this to more general problems, right? So what you have is the integral with respect to from 0 to beta, and the integral with over k of x intersection s of t, right? And you're integrating with respect to d zeta and dt. Okay. So if you remember what we had before, when we had a uniform distribution over a suitably specified set, we had the integral over k of x of 1 times d zeta. Now, when you've got the more general Lord concave density, you've got a double integral. And instead of k of x, you replace this with k of x integral s of t. And this s of t represents the super level set. Okay. And our thought process is similar. Can we now look at this integral, the lower integral, and show by using Lazar's result that it can be then written as the expectation of some other function with respect to a suitably defined density? And it turns out that you can do exactly that. So k of x intersection s of t can be written using, again, the Minkowski functional, and we can write it as the max of zeta transpose x and the Mendowski function with respect to s of t, okay, respect to s of t, where s of t again is a super level set. And so what you find is, instead of the single integral that we had before, now we have a double integral. Okay, that's the big difference. And now what you can see is that by suitably choosing p of psi t, you can say that you can write this as the expectation of f of x psi comma t. Okay, so previously it was f of x psi. Now it's f of x psi t, okay? And the density now is p of psi t. And how do you define this density? It's p of psi, which you can define. And I'm not going to do that here, but it's also another Gaussian density. And you just divide that by beta, okay? So now, if you wanted to solve this problem, instead of simulating using psi, you're going to simulate using psi t. Okay? So now I've shown you how you can deal with log concave densities. Okay, but now how do you move to the next level? How do you start thinking about chance constraint problems, right? So we know that in both cases we can recast the probability distribution function as an expectation. But the problem is that once you do that in the chance constraint regime, you're going to get a problem like this. So let's think about this. So in the probabilistically constrained regime, you've got this problem on the right, on the top, which is CCP. Now, because this probability can be rewritten as the expectation, and then by taking reciprocals, you can actually write this as a constraint. The constraint you get is h sub j of x. So h sub j of x is entirely equivalent to cj of x. Okay. And all that you've done is you've used the reciprocal, and this is of course using setting A, and hj of x is now a convex function in x. Okay, why is it convex? Because we showed that before. Okay, but now the problem is you've got a situation where you've got expectation valued constraints, and to add further insult to injury, you've actually got a compositional structure. So how do you deal with that? Right, that's not something that most of our current tools can contend with. And so the idea that we're going to be adopting, right, is to use the notion of just looking at this problem as a convex optimization problem. It's not necessarily smooth. And so under a suitable regularity condition, the necessary and sufficient optimality conditions are given by this monotone inclusion. Okay, so this is the monotone inclusion. It turns out that this monotone inclusion is not necessarily simple to handle, right? So essentially all I've done here is I've written out the first order optimality conditions. That's all I've done. Okay. Now, the problem is that if you wanted to resolve to get a zero of this inclusion problem, the challenge is that the map T cannot be efficiently evaluated, since it requires evaluating the reciprocal of the expectation, right? Further, it's not possible for you to get an unbiased gradient of H sub j because you have a reciprocal of the expectation, right? So the same problems that occurred in the original regime also manifest themselves here, right? And so how do you deal with that? Well, the way to deal with that is to think about using a proximal point framework. And so I'm going to just describe that, and then we're going to conclude this presentation. So if you look at this, a very well-known approach for resolving monotone inclusions is to use a proximal point framework, right? So what is a proximal point frame? Most of you will have heard of proximal point techniques in the context of solving optimization problems, right? And the ideas are quite similar in the context of solving inclusion problems, okay, or monotone inclusion problems. And essentially what these problems are, they're generalizations of variational inequality problems. Okay, so essentially in a proximal point scheme, essentially you compute the resolvent of this operator T using the parameter alpha sub k, right? And essentially, and you can have some sort of relaxation scheme where you take the original iterate and you have some sort of averaging between them. I'm not going to get into that here because I just want to give you an intuition. Okay, how do you define the resolvent? The resolvent of z of k is I, which is the identity operator, plus alpha kt inverse of zk. This is just a compact way of saying that zk plus 1, which is the resolvent, is a solution of this strongly monotone inclusion problem. Okay? So it's a solution to the problem where 0 lies in T of z, which is the original monotone operator, plus z minus zk divided by alpha k. Okay, and this second term adds strong monotonicity to the operator. Okay, and so, and as you can imagine, that now that you have a strongly monotone inclusion problem, this resolvent problem gives you a unique solution, right? It's relatively simple to ask that. So standard deterministic monotone inclusion problems can be addressed using this proximal point framework, right? But unfortunately, this resolvent problem is not easy to contend with, right? Because T, as I told you, contains an expectation. Okay, so I can't directly address it, and so the way around that is to use an inexact proximal point method. So the inexact proximal point method essentially says, well, I'm going to basically use the original proximal point method, but instead of using the resolvent, I'm going to use an inexact resolvent. So I'm going to use a resolvent plus some plus some EK, where EK is some random error. And I should note that this EK is not necessarily conditionally unbiased. Okay, it's some error. So the question is, how do you compute this inexact resolvent, right? So the way you compute this inexact resolvent is you apply a stochastic approximation scheme to the resolution of this strongly monotone inclusion problem, which has expectation valued, where the operator is expectation valued. And what is important to note is that that problem is strongly monotone, but you can still deal with the fact that you have a bias by using a variance reduced approach. Okay, and so using that approach, you can get an inexact solution, right? So you run the inner scheme for a fixed but increasing number of steps to get an EK, which in some probabilistic sense is diminishing to 0. And using that, you can recover convergence of the overall scheme, right? So this is, as I said, this is future work that I'm describing. We don't have some of this formalized, but some of this framework of using this, this proximal point frame, that is something that we've done. And if people are interested, I can provide you with a reference. Okay. And so I think I'm right at 45 minutes, which is what I promised Fabien, and I'll conclude with a set of remarks. Right. So the idea that we pursued was to recast the probability of interest as an expectation of a suitably defined integral with a prescribed density. We then show that a suitable composition of this expectation is convex. Okay. Unfortunately, traditional stochastic approximation schemes cannot be adopted for reasons that I mentioned. And the framework that we employ allows us to get near optimal rates for this framework. We quantify the sample complexity, but as I mentioned early on, in this particular setting, we're actually just generating samples that we've from an oracle that is relatively cheap, and it's something that we've constructed. And I also discussed how we intend to contend with probabilistically constrained regimes under log concavity assumptions. So moving beyond the requirement that the uniform distribution requirement. So we have a paper that's available on arXiv. It's under first revision now, so I'm going to be making some modifications. And so we did find some typos after the first review, as is expected, and we might add a few more numerics. But feel free to contact me. If you go to arXiv, that's not quite updated. I think we'll be updating in the next few days. Okay, so I'll stop here and take questions. Thank you again, Fabian, for the invitation. It's a pleasure being here, even if it's online.
Thank you, Uday. You are perfectly on time. You said 45 minutes. You really took just 45 minutes. So it's not random with you. But so I will first ask, is there any question in the audience? I don't see any question in this chat. So if somebody wants to ask a question,
trying to find the chat button to see where I can see it right now. So.
On the chat, I don't see any questions.
Okay.
And I don't see anybody raising his hands, his or her hands. So I guess
really bad fit, but
I guess that you could have taken more time. But okay, so yeah, so if I understand properly, this is the results that you have shown are quite preliminary in the sense that you have not tried many applications with your formulation. But so for the second part, especially, it is quite interesting because I agree that the sample average approximation that people usually use in some of the work they've done with some of the students, you relied on sample average approximation, but when we use quantiles, because basically random chance constraints are basically to use to approximate contrasts that in sample average approximation are sometimes not very efficient.
Yeah.
So so basically what you observed is that as long as you left the log concavity assumption for the distribution, the formulation could achieve more precise results, but you have the issue that you have 1 over n expectation to estimate, so you still have some bias at this point of view. Is my understanding correct?
Yeah, I think it is. I think we've tried to take a pathway that has come from what I see as the easier chance constraint problem, right? The one with uniform distributions and then moving to log concavity. And in all of the cases, our goal is to try and make sure that we're at least coming up with estimators that are converging to an optimal solution of the original problem. And you're right about the stochastic approximation part. So there's been work on stochastic approximation on applied towards chance constraint problems going back to Norkin. But what Norkin did was they smoothed the indicator function and directly applied the stochastic approximation to that problem. Now, unfortunately, what happens is when you do that, you're going to be converging to a stationary point of that problem, because that original problem, now after that smoothing, that problem is non-convex. And so our goal was to obviate that, at least to see to what extent that can be obviated, right? Because the issue is once you do that, you're unable to recover error bounds with the original code. But you're exactly right. I think in terms of the behavior, stochastic approximation, as most of you will testify, is quite quixotic, right? It tends to behave weirdly. if you use variance reduction and when you have access to samples like we did, the behavior starts becoming more and more like a gradient method. Now, I should say this problem is non-smooth, so you're not going to get better than the standard canonical rate of 1 upon square root k. So it's not like you're going to magically start solving problems in really quickly. So I think the best you can get is to be able to achieve the deterministic rate, and I think that's what we were hoping to do. Okay. I know you have your hand up. It's good to see you, Johannes.
Yeah, hi, Uday. Very much enjoy your talk. There is this other way, of course, to get an integrable, something that is relatively nice to integrate, and it's this spherical decomposition idea that we found kind of computationally pretty useful, and René Henrion and others have really developed very detail in specific cases, where your function C is this and that structure, convex in the random variable and things like that. I wonder if, that spherical decomposition has a little bit of weakness in the sense that if the dimension of the random vector is somewhat high, then sampling on a sphere can be a little bit costly. Have high variance, and I wonder if your approach has similar difficulties when the dimension of that random vector goes up, or that's in a direction where you might have an advantage.
So that's really so I know some of this work, but I don't know it as intimately as I should. But I should point out. So I'll loop back with you offline just to see whether there's a recent reference, because I'd be keen on seeing that more, that recent, that work. But I should point out that our work also has these types of constants that show up, and that are based on the dimension. And in particular, let me just show you where they arise. Okay, so for instance, if you look at when we define this expectation here. You see this C here, Johannes? You can see that this C is basically going to be defined using some gamma function, and it's going to use the dimension. So that we cannot get around, unfortunately. So we also have some of these dimension-based constants that show up. I think that so I'd be curious to see what where things are easier or harder in the framework that you mentioned. The sampling is very cheap. We don't have a sampling issue. So that's one good thing, and that's why I feel as if the sample complexity the concerns here are, I think that the bound is useful, tells you something about how we're utilizing information, but there is no, we don't have any. The sampling is by no means expensive. That's not a problem. But hopefully I answered your question.
Yeah, no, that's clear. And the you're sampling in the space of Xi, and Xi is in the same space as the original random vector, right?
Yeah, the dimensionality is the same. The only issue is, the only difference is that it's on a Gaussian. Yeah, it's basically in this particular case a Gaussian random variable.
Because I guess what I'm a little bit worried about when you create this kind of exotic expectation is it rather, does it have a big variance when you estimate it? I think so that is a kind of odd, like sharp in any way, and that's a little hard to see when you look from the formulas. I don't know, have you?
Yeah, no, that's a good question. I should say that one of the problems is that these constants, because you have gamma functions floating around, they're not particularly small, right? So you have to be careful with the analysis, because if the analysis isn't done carefully, what happens is this constants persist and you're not able to actually, they affect your behavior. So I agree with you. I should say it's early days for us in terms of our numerics. We've been spending more time on extending and seeing whether we have a framework that is mathematically rigorous. So our numerics, and you'll see this in the paper as well, we've got numerics on these two sets of test problems, But what we haven't done, I'm pretty honest about this, is that we haven't checked to see how these schemes scale as n becomes larger and larger. Stochastic gradient schemes in general do well with that, but the problem is that this has other issues beyond stochastic gradient type concerns. So we're going to be checking and assessing that, but I don't have an answer that is backed by empirical support. So I don't want to say anything too outlandish. So, but I'm but I expect that there's no free lunch, and we're going to be paying for this pretty soon. So.
Yes. Yes, as you said, probably no free lunch, but so when you mentioned the bias due to the fact that you have one over some expectation, did you observe that the bias is large? Do you have any idea of the bias that is present?
So I just want to make, you faded out of the end, I'm sorry.
You mentioned that you have some bias, and so that doesn't make the sample approximation very tractable. But do we have any idea how bad the bias is? I mean, is it large, or have you been able to have an idea of the magnitude of the bias?
Oh, that's a good question. So I don't have a clear answer to that in a theoretical sense, but what I do have is the following. So for instance, if you just apply, say, standard stochastic approximation, right? Now, if you look at standard stochastic approximation, it's not able to deal with the bias. And you can see basically some of those schemes in at least one of our settings just fails. Now, if you use a batch-based scheme, look at this one, right? If you look, if you look at this scheme, even the batch-based scheme doesn't give you, it also degenerates after a while. And the reason for that is essentially what's happening is that you increased the number of samples, but the batch size is fixed. That bias afflicts the progress of the iterative sequence. And so the only way around that is to make sure that the bias essentially goes to zero. And the way around that is to basically increase the sample size as you keep continuing. Now, in general, if you're solving ML type problems, that becomes difficult, right? Because it affects the computation. It affects if generating those samples is costly, it has it has implications in terms of computational time. We don't have that problem yet. So I'm able to kind of address that, and you can see there is a big difference in terms of the behavior. So I don't have an answer to you in a rigorous sense about the bias, but what I do know is that it does afflict kind of naive implementations of stochastic approximation.
That's interesting. But in some way, in the batch essay, does it mean that we should rely on some kind of adaptive sampling strategy to increase the sample when we start to see that there is no really improvement?
Yeah, that's a good question, whether you can use adaptive. So at this point, of course, as you know, when you start getting into adaptive sampling, then the analysis is significantly more complicated, right? Because you have dependent. At this point, we have our sampling strategy is deterministic, right? And that at least allows us to get, from what we see, at least it allows us to do reasonably well. But you're right. I think the next step is to really look at adaptive sampling. To be frank, Fabian, because sampling is so cheap here, we're less worried about it.
Yeah.
So because we've, the expectation is over with respect to a density that we've constructed, and we can actually modify certain aspects of it. So that part is quite cheap. So that has been less of a concern for us. But I think more generally in stochastic approximation, that is indeed a question.
I see. Interesting. Yeah, interesting talk. A lot of things to think about. Thank you very much, Uday. I think it is 3:30. So, is there any additional question? Maybe goes in.
Yeah, I was just wondering, but first of all, great talk, thank you. So because you have this distribution, you constructed it, I mean, maybe you mentioned it and I missed it. I'm just wondering, does this lend itself to some kind of like a, easy bias reduction or variance reduction, in the sense of like you can tilt the distribution even more, something like that? Maybe you mentioned it and I missed it, so I'm just wondering about that.
So you're right. Yeah. So when we chose the distribution, so let me just remind you how we got the distribution and why there's some play here. So essentially what happens is the first step, essentially you're able to show that the probability can be written as this integral, right? Now, once you have this integral, right, it's just e raised to minus g psi. So I can divide and multiply by any positive density, okay? And so I can write this as an expectation with respect to any symmetric density. But the issue is that this g psi in our case has this exponential structure. So we wanted to use a Gaussian because in using a Gaussian, there are some other analytical aspects that become easier. In particular, computing the Clark generalized gradient. There are lots of other things that emerge. And so the flexibility that is afforded to us by choosing this density, we use it to pick the Gaussian. Okay. Now, to your point, can you choose the variance of the Gaussian in a different fashion? The variance actually is bounded in a certain way. I can't be arbitrary about it. The choice of that sigma squared is not something that I can just pick randomly, because I need some. There's some, based on the analysis, there are some lower bounds. So I can't make it arbitrarily tight or something. So I can't do that. And I think in some ways that's if we could, I almost believe that would be a mistake, because there would be it's almost like a free lunch looming there. That somehow you can somehow magically wish away all the uncertainty. But no, unfortunately, there is a So was that your question? That suppose if you have
I'm just wondering if there's further research, maybe, I don't know, because you have all this nice distributions and this reformulation. I wonder how it can be more useful, or if it can be exploited more or something like that. Yeah, so there might be some play in the constants that we can work with, but essentially this is the kind of density we end up with. There might be some other kind of tuning we could do, right? Yeah, I wonder if you could write the variance of it analytically, and then you minimize the variance. I don't know, it can give you some kind of something like that. But
so one thing is that if we have to be careful there, because the issue is that we still need to maintain equality with respect to the original event, original probability. So the parameters can't be fidgeted with too much, right? So we can do a bit, but I don't think we have too much. But
I'm just wondering,
that's a good question. I think, by the way, in the vein of, since you brought up, another question that we've been interested in is this question of distributional robustness. So suppose I looked at the original problem and I said I wanted to minimize the worst case of this probability. We also believe that problem can be reduced to a problem by minimizing the worst case of an expectation over a set of these densities. I didn't mention that here, but I think there might be pathways there, but I don't know as much about the work. I mean, I know there is work on distributionally robust chance constraint optimization. I'm not as familiar with the.
Usually there's some reformulations using the original, but change the, what the probability you're looking into or something like that. So I'm pretty sure it's, you can push through this in that setting as well.
Thank you for the question.
Well, thank you for the presentation.
Thank you, Cousine.
Very nice.
Any additional questions? Otherwise, what I would suggest is that if there is any person wanted to continue the discussion with Uday, we can join the breakout room number 1.